Good day! With this video lesson, we're going to discuss the topic Pearson's sample correlation coefficient. Our lesson objectives. At the end of this lesson, you are expected to calculate the Pearson's sample correlation coefficient, solves problems involving correlation analysis. So let's deal now with this slide, the definition. So the Pearson's correlation coefficient for a collection of n, no, which is your sample size pairs, no, which is your x and y of the numbers is the sample is the number r given by the formula. So we simply use r, no, to represent your Pearson's correlation coefficient. So as you can see, no, on this formula being given to us, no, that your r is equal to ss sub of your xy, no, all over your square root of ss, no, of xx and ss of your yy. So there's a given formula for your ss xy, then your ss sub xx and ss sub yy. So here for your ss sub xxx and ssyyy, then for your ss sub your xy. Here in this formula, you need to get the summation of your x square. So in each value of your x, we need to take the square of these values. Then for us to get the value of the summation of x square. Then for the summation of your y square, no, we really need to take the square of each of the y values that we have now in your table, for example, and for us to get the value of your summation of y squared. Same thing with your summation of x and summation of y. So we just simply get the total of all your x values and all of your y values under your table, and that will be your summation of x and summation of y. Now, for this part, no, your summation of xy, we just simply parted your x sub 1 to your y sub 1. So we simply multiply this x sub 1 by y sub 1, x sub 2 to y sub 2. And uh, after the process, no, we get the products of these two variables being involved, your x and y. So we just simply get the total or sum of these products from your x and y variable. And that's it. No, that will be your third formula that we're going to apply, no, or we're going to substitute as a value in your Pearson's correlation coefficient. So in the previous lesson, no, we learned about bivariate data. No, we also learned how to draw the scatter plot, no, of the pairs of variables, and interpret it qualitatively in terms of its direction and strength. So we simply that's why there is a positive and negative, no, of association using the trends of points. So we just simply assess, no, the behavior of your data by simply assessing the trends of the points. So sometimes a scatter plot, no, does not evidently show that a correlation exists, no, between the two variables. This is in the case of a very weak correlation where it would be very difficult to identify um, the trend line. No, so thus no, because of that, no, we need to come up with more accurate interpretation of the scatter plot using quantitative methods. So here we will compute some values, no, that will indicate a correlation between the two variables exists and describe its strength using the arbitrary scale, which we will make, no. So we need to embrace yourself to the next for this no, for the first example right after this uh, slide, no. So we just simply, use this one, For example, if we can't find, or react, with our scatter plot, because the way we plot your dots is not something that we cannot identify if that is a positive or negative, because of the scattered points or dots that we plot, in your Cartesian plane. Using your Cartesian plane, then we plot your so with the very weak correlation, we need to apply this person's correlation coefficient, especially, once we did not uh, visualize, even if we plot all the given values of your x and y and their corresponding values of y, if we did not even visualize, what will be our so we just simply use this person's correlation coefficient for us to identify, if there is an existing uh, correlation between the two variables involved. So the person's correlation coefficient has the following properties. First, the value of r lies between -1 and +1, inclusive. So you need to take note of this one. So the value of r lies between negative and +1 only. So there is no such thing that the value of your r is less than, -1 and more than +1. So the sign of r indicates the direction of the linear relationship between your x and y for number 2. So if r is less than 0, then y tends to decrease as x is increased. So we simply know, well, once your x increases, then it's automatic that your y decreases if your r is less than 0. That's how we assess that. Now for letter B, if r is greater than 0, then y tends to increase at x is increased. So meaning to say, once your r is greater than 0, if your x increases, your y also increases. Then for number 3, so the size of r, or the absolute value of r, indicates the strength of the linear relationship between your x and y. So for example, if your r is equal to negative 0.65, 0.65, that will be your strength. So whatever the absolute value of this one, if your computed r is negative 0.65, then the value of your strength is 0.65. So that's the absolute value of your negative 0.65. If the absolute value of r is near 1, that is, if r is near either 1 or -1, then the linear relationship between your xy is strong. So if your value of your r, or the absolute value of your r is near 1, so it can be because we're looking, to the absolute value. So we're not subjecting the value with the sign, being involved. We just our concern now is to look for the absolute value of your r. So if the absolute value of your r is near 1, eh, then the linear relationship between your x and y is strong. So that will be our summary for this letter A. If the absolute value of r is near 1, regardless of his sign, because we're looking only for the absolute value of r. Then for letter B, if the absolute value of r is near 0, that is, if r is near 0 of either signs, so it can be negative or positive, then the linear relationship between x and y is weak. As long that the absolute value of your r, will fall, no, nearly or approximately, no, equal to 0, then the linear relationship between your x and y is weak. So these are two conditions that we need to consider, no, for us to identify if the linear relationship between your x and y is strong or a weak, no. It depends on the absolute value of your r. So in this table below shows the verbal description of the strength of the correlation between two variables. No. So here there is a given range of value or values of r here. So in each value of r or range of values of r, so there is a corresponding linear relationship or description of linear relationship. No, from 0 to 0.19. So that will be a very weak positive. So the value or the range inside your parentheses. So there is a corresponding uh, description here or linear relationship from negative 0.19 to 0. So that will be a negative correlation. So for 0.20 to 0.39, so that will be a weak positive correlation. Now, for a negative 0.39 to negative 0.20, that will be a negative correlation. Now, for the third values or range, no, with this one, so 0.40, no, we just simply use a 0.40 to 0.59, that will be a moderate positive correlation. And from negative 0.59 to 0.40, so that will be a negative, no, moderate negative correlation. So we just simply replace lang your positive here, no, in the description. So 0.60 to 0.79, so that will be a strong positive correlation. From negative 0.79 to negative 0.60, that will be a strong negative correlation. Now, from 0.80 to 1.0, that will be a very strong positive correlation. Then negative 1 to negative 0.80, that will be a very strong negative correlation. Why is that it is very strong? Because the absolute value nearly fall, no, on equal to 1, because we are looking for the absolute value, no. The sign represent if that is a negative or a positive. But again, we are looking for a positive uh, absolute value. I mean, no. So let's talk about now more about your positive a correlation. No. So in a positive correlation, no, if a positive correlation exists, no, when high values of one variable correspond to a high values in the other variable, or low values in one variable correspond to low values in the other variable. So meaning to say, no, meaning to say that the slope of your line, or we're going to use the slope of the line, no, and that is a positive slope, no. Once you're dealing with a positive correlation, once you're dealing with a negative correlation, so exists when high values in one variable correspond to a low value in the other variable, or low values in one variable correspond to high values in the other variable. Meaning to say, it is a relationship, no, between your high value to low value or low value to high value. That's a negative correlation, no. So we don't limit your positive and negative correlation, no, for positive and negative correlation, but we also have your zero correlation. So when we say zero correlation, no, It exists when high values in one variable correspond to either high or low values in the other variable. So I mean, say if one value of x can provide you uh, two values of y, or two values of y can only provide you a one value of x, so that's a zero correlation. So I mean, say that there is should be a one-to-one, no? Most probably it should be a one-to-one relationship. But if that's happened, no, that the high values in one variable correspond to either high or low values in the other variable, and that's it. That is a zero uh, correlation. So for this slide, so the closer the value of r to 1 or negative ones, the stronger the relationships between the variables. This can be shown in the diagram below. Now, for us to identify the relationship, between your two variables involved, uh, should be the absolute value of r, no, and nearly, no, should be near, no. The values of the absolute value of r should fall near to uh, a positive one. So here, no, as you can see in this in these values, there's a positive or negative one here. Your positive and negative sign here will represent the direction, no, of your line, no. If that is a positive, then your line, as you can see in the red line here, your line is your line rises from left to right, no? Your line rises from left to right. If your m or your slope, if that is a negative value, no, then your line falls from left to right. So in this one, if your r is nearly or approximately equal to a 1, no, positive 1, meaning to say that your line that the line that we use, no, rises from left to right. This is 45 degrees from your x and 45 degrees on your y, and there is an equation of x is equal to y, meaning to say that in every point that will fall, no, in this line, no, has the same values of horizontal and vertical distance from your x and y axis. Why is that we consider this one as a strong positive linear correlation? Because most of our points, no, here, no, in this graph, most of our points are most of our points falls exactly, on the red line. Mean to say they falls most of the point, if that's happen, no, if most of the points falls, no, on the red line, and it follows uh a positive direction, no, when your line rises, no, from left to right, and that's a strong positive linear correlation. So same thing with a negative correlation. So most of your points falls exactly on your line, no, but not all, but most of the points, no. Then if that if that's happened, no, then your points follow a direction, no, that the line falls from left to right, then that's a strong negative linear correlation. Once we use a line, no, here, no, this red line here, that that will serve as a linear. That's why we called it linear correlation, because we simply use line from the word linear, no, even if your line, no. So the equation of your line is a linear equation. That's why if we use line here, that's a linear correlation. So here, no, in your figure letter C, no linear correlation, in a sense that, for example, if this is your x, no, this is your x and this is your y. So meaning to say that one value of x can provide you two values of y. If that's happened, no, meaning to say if most of our data will behave, no, or if most of our points, no, behave like this, no, that a value of x, no, can provide two values of y, or two values of y can provide you only one value of x. So meaning to say that there is no linear correlation, no, being involved on this figure. So you need to check all of these, no. Then for letter D, weak to medium positive linear correlation. Why you consider this as a weak to medium positive correlation? Because some of your points, no, did not fall, no, exactly on your line, but it follows a behavior wherein we can apply a positive slope. That's why it is considered as a weak to medium positive linear correlation. So same thing with this letter C, no? As you can see, no, our line did not follow I mean, the points that, all blue points here did not follow a positive or a negative slope. That's why it's a no linear correlation. So it's a horizontal line. So once we apply the concept of a zero correlation, so we can prove that this figure is a zero correlation or no linear correlation. So for letter E, weak to medium negative linear correlation. So same thing with the weak to medium positive linear correlation, no? In this one, most of our points did not fall exactly on your line, but they follows, no, a negative slope that falls from left to right. So that's why we consider this weak to medium negative linear correlation. So how about some no linear correlation? Here, no, in this example, no, with the given values of r, no, you need to consider always the value of your r, and there's a given table here, no. For no linear correlation, meaning to say that there is no straight line here, and it follows a curve. As you can see, it is a parabola, no, that opens upward. So at some point here, no, even if your x increases, no, at some point here, when your x increases, your y decreases. But at some point here, when your x increases, your y decreases. And again, at some point here, no, when your x increases, and that's the time at some point here, no, when your x increases, your y increases also. So at some point there are lapses here, so there is no pattern, no, in a way that if your x increases, your y automatically increases, and if your x decreases, your y automatically decreases. So at this point, no, there is a variation between the values of your y. If x increases, your y, from a small value of x, there's a higher value of your y here. For a higher value of x here, there is a smaller value of y. But a higher value of x here, there is a smaller value of y here. So I mean, say there is a variation of no, there in the values of y, even if your x increases. So there is no such thing here that we can pattern that if your x increases, your y also increases. If your x decreases, your y also decreases. So there is no such thing in this graph. So that's why we consider this as a nonlinear correlation, in a way that your points follow a behavior like a parabola or any curve. No. So for example number 1, so we're asked to compute the linear correlation coefficient for the height and weight as shown in the table below. So there is a given value of height and weight. So there is a corresponding value of x and y here. So in each value of x, there's a corresponding value of y, or in each value of height, there's a corresponding value of weight. So for the solution, so we just simply tabulate the given values for your height and weight, or your x and y variables. So for step number 1, we need to construct a table with the components x, y, x squared, xy, and y squared on the top, and with the corresponding values as shown. So for us, it will serve as a guide, no? Your x, y, x squared, xy, and y squared here at the top of your table. So less confusion for our part, no? So we need to tabulate all the given values. Then we need to list down all the given values for your x in your second column here. Then for your y in your third column, and in your fourth column, I mean, no. So that will be the square of these values, no, under your second column. So that will be 68 multiplied by 68. So that will be 4624. 69 multiplied by 69 is equal to 4761, and so on. So for the values, no, under to your fifth column here, no, so that will be the product between your second column and your third column, or the product between your x and y variables. So that will be your fifth column. So under your sixth column, y square, no, so your y square here is the square of these values under your third column. So we just simply get the square of this one. So that will be 151 multiplied by 151. So that will be equal to 22801. Same thing with 146 multiplied by 146. So that will be 21316, and so on up to the last value. And for this last row, no, as you can see in the table, so that will be the summation of all values under your table, or under in each column, no. So we just simply get the total, no, of the sum, or sum, no, of the values under each column. So that will be the summation of x, summation of y, summation of x squared, summation of xy, and summation of y squared, that we really need to compute, because we're going to substitute these values to our given formula for the Pearson coefficient correlation. Correlation coefficient, I mean. So for step number 2, compute for SS sub XX and SS sub XY and SS sub YY. So there's a given formula here. So we just simply substitute the given values for your summation of x squared and summation of x. Then we can arrive to 46.916167. That will be the value of your SSXX. And for SS sub XY, so that will be the summation of XY, and we need the summation of x and summation of y. So from the given values from our table, so we just simply substitute the summation values, and we can arrive to 244.583. So that will be your SS sub xy. Then for your SS sub yy, so that will be summation of y squared and summation of y here, no? So we just simply substitute the given values under your table. Then we can arrive to 1690.9167 as the value of your SS sub YY. So with these three values, now we just simply substitute the three values to your given formula for R, for the linear correlation coefficient R. Then as we simplify, no, the values, no, that we substitute on the given formula, our value now is 0.868. So since 0.868, no, nearly fall, no, or it will fall nearly, or it will fall near to 1, no. So since the value of R is greater than 0 or positive, no, weight y, weight y tends to increase as height x is increases. So the value of 0.868 is near 1. So the linear relation between height and weight is strong. That's why, no, if weight increases, no, most probably your height also increases then. But the thing is, in reality, when your height, no, when your weight increases, it doesn't mean that your height also increases. But in this case, with the data that we gathered, no, your y tends to increase as height x is increases. And that is true. When your height increases, it's automatic that your weight also increases. So the relationship between this weight and height is strong. So that will be a strong positive correlation because the computed value here is a positive value. So for example number 2, Calvin, a physics teacher, is interested in determining the relationship between the number of hours students spent on studying the physics final exam and their obtained final scores. He selected a random sample of 8 students in a physics class, so the scores obtained are shown in the table. So we need to interpret and calculate the Pearson's sample correlation coefficient. So with the given values of your number of hours spent in studying and the score they got, no, and that we can map on the number of spent or the number of hours spent in studying, that will be your x variable, and the score, that will be your y variable. So we just simply follow the table, no? From same thing with the example number 1. So we just simply list down the given values for x and y. So for the solution, so step number 1, construct a table with the components, your x, y, x squared, x, y, and y squared on the top and with the corresponding values as shown. So this will serve as our guide, no? Less confusion for our part. So we need to put here. So number, so we can put number here, no? For the less confusion, no? So here in your second column here, so that will be your x variable. In your third column here, that will be your y variable. So in your fourth column, so we just simply multiply this 1 by 70, so that will be equal to 70. 3 multiplied by 79, that will be equal to 237, and so on up to the last value. Now, in your fifth column, so that will be x squared. So we just simply take the square of these values under your second column. So that will be 1 multiplied by 1. That's why it's 1. So 3 multiplied by 3. So that will be equal to 9. And so on up to the last value. And for the sixth column here, so we just simply take the square of these values under your third column. So whatever the square of 70, 79, 90, 77, 85, 81, 75, 64. So that will be a value of your sixth column here. So 70 multiplied by 70 is equal to 4979 multiplied by 79. So that will be 6241. So that will be your sixth column. In the last row in this given table, no, so your 2621, 1644, 68, 46, 48677. So those are values that we can map, no, as the sum or total of the values under each uh, columns, no, from this table. So we just simply get the values, no, or the summation of this one, and we can get this one, these values, no, for us to compute for the value of the correlation coefficient. So for step number 2, so we're asked to compute the SS sub XX, SS sub XY, and your SS sub YY. So we need to go with your SS sub XX. Then as we substitute the given values from our given table, no? And we simplify, then we arrive from 18. From your SS sub xy, we simply substitute the given values to your table or computed summations on the given table. Then we can arrive to 91.5. Your SS sub yy, or summation of y squared here, minus 1 over n, or the sample size, multiplied by summation of y squared, no? As we substitute the given values from our table, then we simplify, then we arrive from 471.875 as the value of your SS sub YY. Now, for step number 3, no, we just simply substitute the value of your SS sub XX, SS sub XY, and SS sub YY to the given formula for your coefficient correlation. Correlation coefficient, I mean, no, that will be your R. So as we substitute the three values and we simplify these fractions, no, then we arrive to 0.9928. So for the interpretation, no, since the value of R is positive and close to 1, so the variable have a very strong positive correlation. So it means that student students who took more R's in studying get higher P6 score. So when the number of hours spent, no, in studying increases, the score in their P6 subject also increases. So that will be a very strong positive correlation because the value of R, or the absolute value of R, no, um, is approximately equal to 1. And the sign of this R now, the sign of this R is a positive. That's why it's a very strong positive correlation. So in this, for your activity, no, in this video lesson, for number 1, in the interpretation of a computed R, what two elements should be emphasized? Number 2, what are the indicators of these elements? Number 3, how do we make our interpretation of the strength of association more objective? So thanks for watching. If you want to like, comment, share, and subscribe, so please do so. I'm Marvin Enriquez, your subject teacher for probability and statistics.